Have you ever watched a skilled artisan or athlete move with incredible fluidity, seemingly without effort? It is a seamless flow of motion that appears almost magical. Now, imagine a robot trying to achieve that same grace. Unwanted jerk in robot motion is primarily caused by abrupt, sudden changes in a robot's acceleration. Think of it as the rate at which acceleration itself changes. When this rate is high, it creates those unpleasant, jarring movements. The core reason lies in the physics of motion. Jerk is formally known as the third derivative of position with respect to time, following position, velocity, and acceleration. High jerk values mean the forces acting on the robot are changing very quickly. This rapid change can lead to several problems. Mechanically, it causes increased wear and tear on components, potentially shortening the robot's lifespan. Operationally, it can induce vibrations, making precise tasks difficult or impossible, and even compromise the stability of the robot or the object it is manipulating. Moreover, it wastes energy and can be hazardous in collaborative human-robot environments. Think of hitting the brakes and accelerator aggressively in a car. It is uncomfortable and inefficient. Several factors contribute to these sudden changes. One major culprit is inadequate path planning. If a robot's planned trajectory does not explicitly consider jerk limits, it might command instantaneous changes in acceleration that the physical system simply cannot handle smoothly. Another factor can be limitations in the control system itself. Basic proportional integral derivative or PID controllers, for example, might struggle to smoothly transition between different acceleration profiles without generating some jerk. Actuator limitations also play a role. If the robot's motors or other actuators cannot respond precisely and quickly enough to acceleration commands, or if they overcompensate, it can induce jerk. Additionally, mechanical resonance within the robot's structure can amplify jerk, turning a small command fluctuation into a significant vibration. Even external disturbances or poorly tuned control parameters can contribute to this unwanted motion. To mitigate unwanted jerk, engineers often employ advanced path planning algorithms that explicitly optimize for smoother acceleration transitions. These algorithms, such as those generating S-curve trajectories, splines, or B-splines, ensure that the commanded acceleration changes gradually over time. Utilizing more sophisticated control strategies, beyond simple PID, like feed-forward control or adaptive control, can also help the robot anticipate and compensate for changes more effectively. From a mechanical standpoint, designing robots with greater structural stiffness and incorporating damping mechanisms can reduce vibrations caused by jerk. And, of course, meticulous tuning and calibration of the robot's control system are paramount to achieving that desired fluidity. This focus on jerk control is not just about extending robot life or improving precision. It is also crucial for human-robot interaction. In collaborative robotics, where robots work alongside people, minimizing jerk is essential for safety and user comfort. Imagine a robot handing you a tool. If its movements are jerky, it feels unpredictable and potentially unsafe. Smooth, jerk-limited motion builds trust and makes the interaction feel more natural, almost like working with another person. This is why many advanced industrial and collaborative robot programming environments now include explicit parameters for setting jerk limits during trajectory generation, ensuring a predictable and reassuring interaction. Understanding the causes of unwanted jerk and implementing strategies to reduce it transforms a robot from a purely functional machine into a more efficient, safer, and ultimately more capable assistant. By carefully planning movements, refining control, and considering mechanical properties, we can help robots achieve a level of fluidity that truly mimics human dexterity, unlocking new possibilities in manufacturing, healthcare, and beyond. It is all about mastering the nuances of motion to create seamless, intelligent automation.
If you love robotics, Like, subscribe, and keep building with us.